Okay, so in the previous classes, I taught you about the spring and damper and the RC circuits, and as a first order system, just giving you a summarize what we have done. This is the spring and damper, right? And this is KF, KC, and I showed that this is called with RC circuits, RC circuits. Here we go. V in RC, because both of them they had the output over input of closed loop transfer function of 1 over tau is plus 1. So tau is time constant. Tau is time constant, right? And for both cases, I showed you mathematically and in MATLAB and simulating the both that if the input is in the form of impulse, output is gonna be this, so output follows the input, so ESS for the impulse input is 0. Then I showed that if the input to the system is ramp, is a step, unit step, the output of the system gonna be this without any oscillation. So again, ESS steady state error signal is 0. And also I showed you that if the input to the system is the ramp, right? So like this. So the output of the system, as I showed in MATLAB simulating mathematically, as a steady state constant error signal. Here we go. After turn response. So, and we calculated that and we saw that the ESS steady state error signal was tau. Right? So today I'm gonna complete the loop and we are done with the first order system, except that we're gonna go to frequency response. So today I'm gonna talk about the last first order system. So tank of the water, tank of the fluid, say, not water. So you have a inlet flow rate Q in instantaneous, outlet flow rate Q out. So inlet flow rate and outlet flow rate, they are affecting on the height of the water, the fluid. So H. And this contraction acts as a resistance, because the resistor of electrical circuit, you're saying of the R of T, R of tank. Obviously, every tank has a capacity, like as capacitor of a RC circuit. We are saying as CT, capacitor of the tank. Clear? So the goal is that we derive the differential equation in the first order system, and finally we apply the parabolic input to that system. So what we're gonna do, I want to see what's Q in over H. This is our closed loop transfer function. Or I want to see this exactly reverse. H over Q in. Maybe we calculate other transfer functions. Output is the H, with the Q in is the input to the system. This is closed loop transfer function. So, saying that in the electric circuit, we know that the Ohm law, it says the voltage equals to resistance in the current. So guys, what's the meaning of the voltage in mechanical engineering? You let me know. What's the meaning of the voltage? Why we are saying plus? Why we are saying here is minus? and the current is being from the high potential to low potential. That's right. What's the meaning of the V? Potential. So V is potential. That's right. V, voltage, means potential. Potential. Like that, you have in a dynamic course that you pass in ME220, if you have a ball here, if you release that, it's going to come down. That's right, without any force. So this is from high level to the low level, to the ground. So you see that the potential also is here. So look at this tank of the fluid. What's the potential here? Q in, CT, RT, Q out, H, based on whatever defined. And based on this example. What's the potential? Yes, exactly. So in the analogy with that, you say that here I'm exactly writing like this. It's gonna be H equals to, the name of this course is modeling of physical system. We have to learn how to, in analogy, how to model systems, and at the end we say that these systems, they are equal. What is the resistor in the electric circuit, and what's here? What's this? Valve. Resistance of the valve. This is valve. This is valve. Okay? This is valve. So valve, like as your kitchen valve is RT. Valve that you are opening in your sink in the kitchen is RT. Understand what I'm talking about? Yes? And what is I here? Current. Current in the tank of the fluid. Which current is depends on the R here? Look at here. Current is Q in and Q out, right? Which of them is directly affected by the RT? RT. Yes. Q out. Relation number one. But before going ahead, okay, I want to take you to one of my, I have done this research in 14 years ago when I was a PhD student at Villanova University, and I'm working on a project sponsored by the ONR, Office of Naval Research. So this is my lab website, you know that, right? So I have a very famous robotic lab. If you don't know, so we have a quadruped robot here. See that? Hold on. See, like this. Maybe you have seen that, huh? So okay, and too many things here. Okay, manipulators and this kind of things. Okay, so let me open it for you. These are my publications. Look at this. Chaotic and hyperchaotic dynamics of smart valves system subject to a sudden contraction. I'm just opening this. We published in ASME Journal of Dynamic System Measurement Control, or ASME Journal of Dynamics. So this published in 2016. Okay, guys, look at here. There are two butterfly valves Do you see here? Yes? We modeled based on the course that I'm teaching you. We modeled as the resistors, changing resistors. This means changing R1 and R2. See, R1 and R2. You see, if I come down here, let me show you. Here we go. I modeled based on the course I'm teaching you, the valve as the resistors, R1 and R2, that they are function of the angle of the valves. I don't want to teach this because this is high level for you. But I'm saying that what I'm teaching you are using in the research. And that ended to the pressure after the valves, that is huge based on the resistors. And we ended up with the state space equations that I taught you in the math labs. Do you see that? Z.1, Z2, Z.2 is a nonlinear term based on the resistors or the valves. And finally here. I just want to teach you that for whatever I'm teaching you can use in the research eventually. In the linear domain, obviously. Okay? See what I'm saying? So, let's go ahead. So now, relation number 1. Now, can I go to the next page?
Yeah.
Relation number 2. In the RC circuit, I talked to you about this for the capacitor. I is equal to C dV in dVc over dt. Remember? That's right. This is for the capacitor. So, based on the name of the course, we have to find an analogy between this and the tank of the fluid. So obviously this side, this C is what here? Capacitor. Look at this figure. Yes, CT, tank capacitor. Capacity, CT. D over dt. So we said, what is the voltage? What is the voltage? What is the voltage? H. And I. Okay? So when we, here, listen to me very carefully. When we want to say that I, is I associated with the resistor. But when I'm talking about the capacitor, the I affecting on the capacity of the tank. So which of them affects on the capacity of the tank? Q in or Q out? Change of which of them changes the capacity of the tank? Simply saying. Both. So you have to say is the net flow. Means Q in minus Q out. See what I'm saying? Because it's in plus out minus is out of the tank. So it's going to be net flow to the tank. See what I'm saying? Everybody? Yes? So this is relation number 2. Having this, H equals to R of the tank, Q out, and CT dH over dt equals to Q in minus Q out. Okay? What I'm going to do, I'm going to put Q out here. What is Q out? Q out equals H over RT. So CT dH over dt, I'm moving Q out to other side, plus H over RT equals to Q in. So what I'm going to do, I'm going to multiply both sides by the CT. So you're going to have dH over dt plus 1 over RT CT H equals to Q in over CT. Okay. So now we're gonna transfer this to the frequency domain, guys. Laplace. Okay. So we're gonna have H of S plus 1 over RT CT H of S is Q in over CT, or the closed transfer function is H of S divided by Q in is equal to 1 over CT S plus 1 over CT RT. Okay? Understand, guys? And this is the first order system, as I promised you. And now if I say my closed transfer function is Q out over Q in, I want to find this. Okay? If I do that, you have to replace this here. H in D, CT DH over DT. When you are done, I will move that. I will go to the next page. Can I? Okay. So it's gonna be CT D over DT. Your H was RT Q out equals, look at here, Q in minus Q out. Q in minus Q out. Obviously, this CT-RT is going to be dQ out because RT is constant over dt. Q in minus Q out. Moving Q out to the other side because CT RT dQ out over dt plus Q out equals to Q in. We're going to see, as I told you, in the right hand side of the differential equation is the force or excitation to the system. Left hand side is the dynamics of the system. You want to see effect of the Q in over the Q out. Bingo. Laplace. So you're going to have CT RT Q out plus Q out is, and you have S here, guys. S because of the first time derivative equals to Q in. Simply saying that Q out over Q in, output over input, is 1 over CT RTS plus 1. And this is our standard first order differential equation. And what's the name of this, guys? CTRT? What's the name of this in the first order systems? Yes, exactly like this. It is time constant of the tank of the fluid. So Q out or Qn gonna be 1 over tau of the tank S plus 1. So it's time constant of the tank is the capacitor of the tank multiplied by the resistance of the valve. You see that this very beautiful analogy between the systems. And now nothing changes when we go to the MATLAB and Simulink. So plus minus, here you have to put the open loop transfer function G. So it's gonna be Q out, it's gonna be Q in, and I told you a million times from here the open loop transfer function is being found from G over 1 plus G for the unity feedback. So it's gonna be 1 over tau of the tank S, as we did for the previous cases. Understand, everyone? Yes? Huh? So if you're done, I will move to the next page. I mean, tau T means the tank time constant. Okay, this is under the script. That's right. Tau, tau, tau. I guess. Yeah. Tau of tank. Can I go to the next page? So, being said, now as I promised you, you can say spring and damper is the RC circuit is the dynamics of that, obviously, is the tank of the fluid K, C, KF, V in, RC, and Q out. They all are first order systems. With the transfer function of output over input, generally speaking, 1 over tau S plus 1. So if you want to control a spring and damper system, you want to design a digital controller, you want to make a board, RC circuit does the same job. Have an RC circuit and then calibrate the forces with the voltage. I'm not kidding, I'm serious. Calibration. The name is calibration. Calibrate force with the voltage and the time constant of KC and RC, and then you can control this by a board of RC circuit. If you want to control the output over input of this, control it, not only model that with it. Just make an RC circuit, calibrate, H with the V or Q out, whatever you want, okay? Then control it. And whatever I taught you that the input is the impulse, input is the step, input is the ramp, is also valid for the tank of the fluid. For the impulse, steady state error signal is 0. For the steady state signal is 0. For the ramp has a steady state of, for the ramp, ESS is tau S, tau tank, I'm sorry. For the ramp. For the ramp, ESS is tau t. Now let's go for the last input to the system, D, for now. When Qin is, sorry guys, when Qin is parabolic. So when I say that for all these systems, this is valid because they have the same dynamics. See what I'm saying? Yes. So we know that if you apply the Laplace based on the table that I provided, Q in gonna be 1 over S cubed. I'm gonna put it here. So the output Q out that over Q in was 1 over tau of tank S plus 1. So you get from here that the Q out is 1 over S cubed, 1 over tau S tank plus 1. As we did for the previous cases, now you can write this as, because we have 3 poles, S cubed means 3 poles, that's right, at the origin of the complex plane, real, imaginary. So S3 means that 3 poles at the origin, 1, 2, 3. We cannot eliminate those, because if you solve this, you have to say P1 is 0 because it's third order, P2 is 0, P3 is 0. So you have 3 poles at this. Another pole is here. See? For the formula transformation. Minus 1 over tau. So you disclose the transfer function, Q out, has 4 poles. So it's 1 over S cubed you have to write, plus B 1 over S squared, you have to write like this, as we did for the ramp. C 1 over S plus D 1 over tau TS plus 1. Clear? You're gonna find A, B, C, D. So you can write this as S cubed tau S plus 1. It's gonna be A in tau T, all of them there T, TTS plus 1 plus BS tau TS plus 1 plus CS squared tau TS plus 1 plus D S cubed. These are tau T, tau T, tau T. This is the most trivial way to find ABCD. And this is equal to how much finally? 1. If you are done, I will go ahead and do that. So, can I? Yes, sir. So, being said, I'm writing here A tau TS plus 1 plus BS tau TS plus 1 plus CS squared tau TS plus 1 plus TS cubed is 1. Obviously you see that, oh, I'm sorry. Okay. So I'm now sorting based on the orders. See? S cubed. S cubed is D plus C tau T. There we go. Plus S square. S square is C, see here, plus B tau T. There we go. Plus S. S is B plus A tau T. And finally you have 1A equals to 1. Being said, you easily understand A is 1. A is 1. If you put it here, you get B as minus tau tank. If you put the B here, you get C as tau T squared. If you put C here, you get D as minus tau T cubed. Clear, everybody? So your outlet flow rate Q out gonna be 1 over S cubed. I'm just putting here 1 over S cubed B C D minus tau T over S squared plus tau T over S minus tau T cubed over tau Ts plus 1. Being said, I want to go back to time. What I have to do, going back to the time, now you know it. Now you know it. You want to go back to time, gonna be inverse. So Q out, outlet flow rate of the tank in time, this is gonna be input to the system, parabolic. This is gonna be ramp, as we know, minus tau T in ramp T. This is gonna be unit step, as we did before, plus tau T as it is. And this is gonna be, you can write this as this. Look at here, guys. Tau T squared in S plus 1 over tau T. So this is gonna be decaying term, that's right. It's gonna be minus tau T squared E minus T over this. Okay, guys, pay attention to me. This is output to the system. What was this to the system? I told you. What was this to the system? Output. What was this we applied to the system? Look at here. What was this? Huh? What was this? Guys? Yes. This is input to the system. This is decaying term. Means when T goes to infinity, as I taught you a million times, this goes to how much? This goes to how much? How much is this when T goes to a large number? 0. Bye-bye. So, I'm saying that I'm moving this to this side. Input minus output. Now, look at here, all of you. All of you look at here. Input minus output is which signal here? What signal here we have? Also error signal, E. So this is gonna be E of t equals to, I'm moving these to other side, tau t minus tau t. So the error signal when you apply the parabolic input is a error signal, and it shows when time increases. When time increases, see, time, error signal increases. When time goes to infinity, error signal eventually will go to infinity. So despite the input of the ramp in parabolic input, the error signal is not tau. It's unbounded error signal. It increases. Everybody understand? Yes? Yes, guys? Huh? Yes, everybody? Okay, can I go to the next page? Can I, guys? So, we have a mathematical proof. ESS is final value theorem. S Q in 1 plus G when S goes to 0 is the limit of S. Your Q in is parabolic, 1 over S cubed. And this is open loop transfer function, 1 over tau t over S. Look at here, open loop transfer function. When S goes to 0, one of these goes to New York, so you get the limit of 1 over S squared plus S over tau t when S goes to 0. It's going to be 1 over 0. What's 1 over 0 in mathematics, kindergarten mathematics? A large number, infinity. So you see that the steady state error signal here goes to infinity. Understand? Everybody? Being said, if I want to plot this, Q in, Q out, Q out. Q out. So input to the system is parabolic. Oops. Input to the system is parabolic. And we saw that the error signal time increases. See? This is error signal, increases with time. See what I'm saying? So this is Q out. This is Q in. Here we go. Understand, everyone? Yes? And this is error signal, guys. So now we completed the 4 inputs. Now I can plot the table at the end before going to the frequencies response in the next class. I'm gonna say when you apply impulse, you apply the unit step, you apply a ramp, you apply a parabolic. This is input to the system. And the steady state error signal gonna be 0, 0, tau, infinity. For which system? For first order system, 1 over tau s plus 1. When the closed transfer function output over input is this. And this is the summary of the first order systems. Here we go. So you see that for the first order system, before ramp, steady state error signal is 0. But after that, we have steady state error signal. So here, when you go to ME430 that I'm teaching, we're gonna design controller to make these two also to 0. We need controller. I controller. I control. There we go. See what I'm saying? So let's go to the MATLAB, but before going to the MATLAB, also we have to model this. Q out over Q in is 1 over tau of the tank S plus 1. As this is 1 over S cube and MATLAB has no command except step, so you can write this as 1 over S squared in 1 over S. And I taught you 1 over S is which kind of input to the system? We did together 2 times at least. What kind of input to the system? Unit step. So we can write this as this: Q out over 1 over S is equal to 1 over S squared. This comes to this side. This in tau TS plus 1. So you're gonna say Q out over unit step is 1 over tau T S cube plus S cube. So for plotting in MATLAB coding the parabolic, we are changing the transfer function to the third order system, but with the input of the step. Hello everybody? So being said, you get num equals to 0, 0, 0, 1, because this is the third order system. And the then gonna be tau T 1, 0, and 0. Third order system. For example, I'm gonna stick to 2. Tau T is 2. Sorry. Clear everybody? Yes? Okay, now let me go to the MATLAB. Okay. So I'm gonna be clear space, clear all. I'm gonna share it with you. Num equals to 0, 0, 0, 1, and then equals to 2 seconds, or t is tau t is 2, 1, 0, and 0. See, exactly like this. There we go. Okay. So then I'm gonna figure 1 step num then and time. Set me t. And I'm defining t as 15 seconds. Oops. 15 seconds. Okay, t. And I'm gonna say grid. And then I'm gonna say hold on. Then I'm gonna plot input to the system. Input to the system, look at here guys, was half of t squared. That's right. Look at here. Oh, squared. See? T squared. But you have to write the square like this here, guys. If you read like this, it's gonna make you error because this is vector. In vector, you have to put dot square. See what I'm saying here? Do you see here, everybody? Yes? So this is input to the system as parabolic. Here now I'm going to say plot time and input and say red. And then I'm going to put legend. Legend output input. Here we go. And I'm going to save it here. Parabolic response, because I'm going to share with you. Everybody understand? So if I run, let me first debug it. Here we go. As I promised, you see, this is the input to the system, right? And this is the output to the system. As I plotted mathematically, we derived the refiner value theorem. By increasing the time, the error signal, what? You tell me. Error signal increases. See what I'm saying? And obviously you can change the title and say parabolic response. See that we change the transfer function, call the transfer function, but by using a step, we are plotting parabolic response. There we go. Parabolic response. Everybody clear? Yes? Huh? Hello? Okay, now let's go back to here, because when we go to Simulink, as we did previously, I'm going to share with the canvas view. So this is, oh no, this is what? This is the closed transfer function. For the Simulink, you have to go to the open loop transfer function, 1 plus g. So you have here 1 plus g equals to g tau t s cubed plus s squared. So from here you get the open loop transfer function. Okay, you're gonna have 1 over tau t s cubed plus s squared minus 1. So in the Simulink, you have to put this. For example, this is 2. So for the Simulink, you're not gonna be the same. You have -1 here for the Simulink. Because there's no S, but there's a constant number for the Simulink. See what I'm saying? Just open the transfer function. Can I go to Simulink? So being said, I'm opening ramp. Okay. Let's wait until it comes up. Okay. So I'm gonna copy these. I'm putting on the new, because you're gonna have it in the new file here. And you see that I'm gonna change this to, actually you can use ramp, and please do it as a homework, okay? 1, and here I'm gonna 2, 1, 0, and -1. See, the open loop transfer function here is this -1. So having that, let's get this. Okay. Likewise here, and apply. Here we go. Please, as homework, try to change the transfer function and use ramp. Okay, what I'm doing here is step. Okay, and here is step. Okay, and I'm putting this here. And just double checking that the step time is 0. I don't want to have delayed one. Okay, and then saving as parabolic input, parabolic response, and then having that plot scope. Okay, and I don't need marks. Okay, so I don't need this. There we go. Okay, and you see that this is 15 seconds, and that's it. And if we run this, there we go. Parabolic input. If you plot the input to the system, gonna be like as MATLAB coding. Error signal increasing. Everybody understand? But again, put here close loop transfer, open loop transfer function here. I'm writing here to make sure that you follow me. Open loop transfer function. Save. Okay, guys. Done. So I'm gonna now stop this.